Chapter 43, Molecules and Solids. The previous chapter focused on what's going on inside an atom, how electrons behave inside an atom. Now let's go outside one single atom to see how different atoms can form a molecule through what's called molecular bonding, and then how molecules, a large number of molecules, can bond together to form a solid. When you look at how atoms form molecules through molecular bonding, we are studying what's called quantum chemistry. And then we study how large number of molecules can band together to form solids. We're in the realm of what's called condensed matter physics. And in condensed matter physics, we must deal with not only the quantum nature of these particles, but also what's called quantum statistics, because as you know, statistical physics deals with a large number of particles. Quantum statistics, turns out, is different from what we learned in 1B classical statistics, in the sense that the symmetry or anti-symmetry nature of the particles in question will make a big difference. Whether they are fermions or bosons will make a big difference. We'll see all of that. And also, we're going to look at some important examples of solid state, the so-called semiconductors and superconductors. So now let's begin our first part of this chapter, which is molecular bonding, how atoms can bond together to form a molecule. So let's look at how atoms can tie together to form a molecule. It's called molecular bonds. There are different types of molecular bonds which we'll be studying one after another, but all of these bonds share something in common, and that is the bonding is based on the mechanism of Coulomb force. You have attractive force between different types of charges and negative and repulsive force between the same type of charges. For example, electrons will repel each other, electrons and protons will attract each other, and so on. This is the bonding mechanism. And why do they bond? Why do different atoms bond together to form a molecule? Well, regardless of the bonding mechanism, that is how they actually do it, the goal is the same. And that is, they want to lower the total energy of the system. That is the so-called motivation for the bonding to even exist. So let's consider two atoms. When they're very far apart from each other, they don't see each other. So let's say the energy, the interacting potential energy between them at that very far distance, we define it to be 0. Now, as they get close to each other, under some circumstances, they will form a bond. So it becomes a molecule. For example, the two hydrogen atoms, when they see each other, when they get close enough, they can form an H2 molecule. So what is behind that bonding? The idea is this. These two atoms, when they get very close together, they will feel each other's existence, and they will decide to make a deal. That deal may involve a transfer of an electron from one atom to another, or it could involve sharing electrons. So this guy may contribute an electron, this one may also contribute an electron to be shared by both of them. Or maybe they don't want to either transfer or share electrons, so the electron will remain bound to their parent atoms, but the electronic cloud will be deformed, they will redistribute. Any way you do it, there are different mechanisms, but the goal is always the same. Why do they want to make a deal to form a bond? It's because they want to lower the total energy of the system. So the total energy is now below 0, compared with the case when they were very far apart, the total energy was 0. That is the reason. So if the atoms could talk, they would talk like this. In the name of energy, or more precisely, because we want to save the total energy, lower the total energy, let us make a deal. Electronic transfer or sharing or whatever. That is the essence of molecular bonds. And how do they do that? Through Coulomb force. Well, they do that with different ways. Here is a list of the primary ways they can do that. Ionic bonding, covalent bonding, van der Waals bond, and hydrogen bond. Those are different ones. The ionic bond involves one metal atom and another non-metal atom. Actually, you can have more than one atoms of each kind, but the simplest type would be one metal atom and one non-metal atom, such as common salt, NaCl. Let's see what happens in an ionic bond. The idea behind ionic bonding is very simple. There is a total transfer of an electron, or maybe more than one electron, from the metal atom to the non-metal atom. Here is a metal atom, and here's a non-metal atom. The metal atom transfers an electron or two to the non-metal atom, and then as a result becomes positively charged, and the non-metal atom now becomes negatively charged, and they start to attract each other, and the Coulomb attraction is what's behind this ionic bonding. So why did they do that? Again, there is only one goal to achieve, and that is to lower the total energy of the system. Let's use an example of common salt, NaCl. Na, the sodium, is the metal atom here, and chlorine is the non-metal atom. Now you know sodium has an extra 3s electron at its outermost orbital, that's the valence electron, and it's only loosely bound to the sodium nucleus. Chlorine, on the other hand, needs an extra electron to fill its p level, so that it really wants that electron from the sodium, and sodium doesn't really put up too much of a fight, because that electron is loosely bound to it only. So there is an energy transfer. There is an electron transfer when sodium and chlorine see each other closely. So let's look at the following energy diagram. This is the total energy of the sodium-chlorine system. This line here, when energy is 0, refers to a case of a charge-neutral sodium atom plus a charge-neutral chlorine atom. Suppose we transfer an electron from the sodium to the chlorine. Now the sodium is not completely happy about that, even though it doesn't take too much effort to yank that electron out. In other words, when you transfer an electron from the sodium to chlorine, you don't consider anything else, that actually takes some energy. Okay, it takes some energy. So you put them very far away from each other. This guy is positively charged sodium. This guy is negatively charged chlorine. They do not see each other, but the sodium loses an electron and the chlorine gains an electron. That actually takes energy to do that. So the energy is about 1 eV. It takes about 1 eV to put this electron from here to there. However, because the sodium is now positively charged and the chlorine is now negatively charged, what if you bring them closer together? There is naturally going to be a potential energy which is negative, because that's an attraction between the two atoms, the two ions. So the energy starts to decrease due to the Coulomb attraction. Right? It's a negative potential energy, and at this point, which is about 0.9 something nanometers separation between the two ions, at that particular distance, the negative potential energy due to Coulomb attraction equals to the energy it takes to yank this electron from the sodium to the chlorine. So the game is even at this point. Okay? In other words, at that distance, when they're separated by this far distance, you pull this electron out and give it there, the total energy of the system is the same as if it didn't do that. Now, what if they go further in together? So the distance becomes smaller than that distance. Okay? Gets smaller and smaller and smaller. Then the attractive potential energy gets even lower and lower, so now it becomes negative. Negative means the total energy is now below that of the free charge neutral chlorine plus the free charge neutral sodium. So now there is an energy, energy-wise, there is actually some benefit. The total energy now is lower than before. Isn't that what the particles want to do? Lower, 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 until the separation between them becomes 0.24 nanometers. At that distance, the total potential, the total energy of the two-particle system, NaCl, becomes the lowest. Beyond that, when they get that close, they start to repel each other, and then the total energy rises. So you see, it actually pays for these two guys to have an energy, to have an electron transfer from the sodium to the chlorine, as long as you are lower than that distance, okay, about 0.9 something nanometers, the total energy will be lower than before after the energy transfer, after the electron transfer. And they're going to settle at that distance, about 0.24 nanometers. This is where the total energy is as low as possible. This is where the system is the most stable, and therefore, this is how the ionic bonding is formed, and there's a stable separation between the positive and negative ions at 0.24 nanometers. At that distance, the energy is 4.2 EVs below that of the two free atoms with no energy, no electron transfer. So in order to start from here, the lowest energy state, where the separation is 0.24 nanometers between the two ions, and to give this electron back to sodium so that you can separate these two guys to infinity, you would need 4.2 eV. Okay, 4.2 eV. And at that particular distance, this is where the energy would be the same after you transfer the electron or not. So this is where we call it dissociation happens, because this is where the electron can actually get back from the chlorine to the sodium, yet the system's energy will not make any difference. So this is where you can actually take these two ions apart by giving this electron back to the sodium, so that the two atoms charged neutral can go separate ways. So this is an example of ionic bonding between two atoms in the same molecule. Again, that's when you have one metal atom and another non-metal atom. Now let's look at a second type of bonding, covalent bonding. If we're dealing with two atoms and neither of them is a metallic atom, then neither would be willing to give up any of their electrons. So they're going to start to fight against each other for extra electrons if they need one or two extra electrons to form a complete shell. So what is the outcome then? Well, they have to negotiate, right? And they don't want to give up an electron, but they do want somebody else's electron. So as a result of negotiation, they decide to share some electrons. That is what covalent bonding means. Valent means, here stands for valent electrons. Covalent means they share some of these valent electrons. That's called covalent bonding. So as a result, you got some these shared electrons that are somewhere in between the two nuclei, and that's what ties the two atoms together, forming what's called a covalent bonding. That's a very common type of bonding. An example, H2, the hydrogen molecule. This is a case where the two hydrogen atoms, H, here's one H here, another one, very far away from each other. R is very large, and here is the wave function of the electron cloud for the first hydrogen atom. Here's the second hydrogen atom, and the two wave functions of the two electron clouds, they have basically no overlap because the electrons are too far from each other. They don't see each other. All right. Now, when you bring them closer together, the electron clouds start to overlap, and in that case, we must look at the two electron systems in a very careful manner, because remember, electrons are fermions. So if you look at these two electrons, look at the total wave function of these two electrons, one from each hydrogen atom, they must be anti-symmetrical. The wave function of the two electron system must be anti-symmetrical, meaning that when you exchange these two electrons, you get a negative sign, right? Because these are fermions. Now, the wave function of the two electrons actually consists of two parts. There is a spin part, and there's also a space part. The spin part, that's determined by the total spin. If the spin of the two electrons are oriented in the same way, okay, same way. So you just add the two spins together, S1 and S2, both are equal to 1/2. The total spin equals 1. When the total spin equals 1, then when you exchange the two particles, the spin state does not change, so the spin state becomes symmetrical, which means the space part must be asymmetrical. You can also look at the other way around. If the spin part is anti-symmetrical, which means you exchange the two spins, you get a negative sign, and then in that case, the space part must be symmetrical so that the product remains anti-symmetrical. Right? This is the space part. Here's the spin part. The product must be anti-symmetrical. So let's see here. There are two possible cases then. One is when the spin part is anti-symmetrical so that the space part is symmetrical. This is known as the bonding state. Bonding state. The spin part is anti-symmetrical. Okay, what does that mean? Very simple. Here is the spin state of the first particle, the spin state of the second particle. Here's the first particle, the second particle. So it's up, down, and here's down, up. I'd write down the spin part of the wave function as this minus that. So you can see what happens when you exchange these two particles. Exchange the two particles. First term becomes the second term. Second term becomes the first term. So the entire spin part of the wave function does acquire a negative sign. Okay, so the spin part is anti-symmetrical. You see that requires one spin up, the other spin down. Okay, the total spin is therefore 0, and the spin has z component of 0, whether you look at this state or that state. Either way, the spin state, the total spin along the z-axis has a quantum number of 0. That's the s equals 0 state. And the nice thing about that is that the wave function, the space part of the wave function is symmetrical. So it's like this. Okay, it's like this. And you see this electron, the electrons actually spend quite a bit of time in between the two nuclei, right? Here's one nucleus, here's another, right? You have a large probability for the electrons to appear somewhere in between. And then these electrons are negatively charged. So you have a big cloud of negative charge somewhere in the middle. That encourages this positive charge, the nucleus, to get close to it, encourage the other positive charge to get close to it. And that's how a close bond is formed between these two hydrogen atoms. That's called a bonding state. Okay, this is where the space part of the wave function is symmetrical. We got psi s is psi 1 plus psi 2. Now, you can look at the other case, so-called anti-bonding case. That is where the space part is anti-symmetrical and the spin part is symmetrical. So look at the spin part first. Okay, look at the spin part first. Again, it's the product. Total is the product of spin part and space part. Spin part is symmetrical. You see here. When you have a spin being symmetrical, you have to add the two s's, s1 and s2, have to add them up. Each has a quantum number 1/2. The total spin is equal to 1. So you have total spin equal to 1, and ms therefore has 3 possible values, right? 0, positive 1, and negative 1. These are the 3 ms values. Here, the spin has a z component of negative 1, because it's negative 1/2 plus negative 1/2. Both spins are down. Here, both spins up. ms equals positive 1. And here, ms equals 0. The two particles have opposite spins, and yet, when you exchange these two terms, here's a plus sign, not a negative sign. Okay? These two terms, after exchange, the total wave function of the spin part remains the same. So therefore, these are the 3 possibilities for the spin part when s equals 1. Any one of these will give you a symmetrical spin wave function under the exchange of the two particles. That means the space part must be anti-symmetrical. So here's one wave function for the electron cloud for the first hydrogen atom. Here's the second one. The second one must be anti-symmetrical, must be inverted like this. You can see here the combined wave function is very small. It's actually 0 here. You know what that means? The electron has no chance of being here. And the electron spends very little time here and here because the probability is all low. Okay, it spends most of the time about themselves. So therefore, there is no incentive really for these two hydrogen nuclei, the two protons, to get close to the middle, because there is no electron, there is no frequent appearance of electrons in between. There is no reason for them to get close together, and therefore, this is not a way to bond the hydrogen atoms together to form H2 molecule. This is called anti-bonding. In either case, we can plot the total energy of the two hydrogen atom system as a function of r, the distance between the two protons, or between the two centers of these two atoms. And this is the case of anti-bonding. Anti-bonding means, there is really no bonding mechanism. So the closer they get, the smaller the r, the worse. The total energy is positive, gets higher and higher. There is no reason for them to form an anti-bonding state like that. Okay, but bonding is a different story. For bonding, which is the previous case, right? Which is like this. As the atoms get closer and closer, as r shrinks, the total energy starts to go down. Because again, you have a good chance for the electrons to appear right in between the two positive charged protons. So the protons will try to get close to each other to take care so that they get close to the electrons through a negative potential difference, negative potential energy. So it start to go down, and then when r, the separation between the two protons, reach a value of 0.074 nanometers, you find the total energy becomes the lowest. When you try to get even closer, the electronic repulsion will become more significant, and the total energy goes up. So you see clearly there is a stable equilibrium for the bonding case when the space part wave function is symmetrical versus anti-symmetrical, and that happens when the two protons are separated by a distance of 0.074 nanometers. Now you can compare that with the first Bohr radius, which is 0.053 nanometers. So the two protons actually in this case, they're close enough so that the distance, so that the separation between them is less than twice the Bohr radius. So therefore, the electronic clouds of the two atoms do overlap, and that's what we want. So in the previous two cases of bonding, we saw metallic bonding where there's a total transfer of electron from one atom to another, or covalent bonding where the electrons are shared. Some of the electrons are shared between the two atoms. But that's not all there is to molecular bonding. Sometimes no electron is ever totally transferred or even shared by different atoms. Okay, every electron belongs to exclusively to its parent atom, and yet there still can be a bonding between them. An example would be the van der Waals bonding. In the case of van der Waals bonding, you have two charge-neutral atoms. Two charge-neutral atoms. Electrons do not jump out back and forth. They're not co-shared by any of them. However, there could still be a bonding force between these two atoms. How does that happen? Well, there are three types of van der Waals bondings, but they all share something in common. That is, you have to have what's called an electric dipole. Okay, dipole. What's a dipole? You learned that from physics 1.0. What's a dipole? A dipole is a collection of two charges, one positive, one negative. They're close by to form a polarized region. The total charge is 0, and yet the positive center and negative center are not at the same locations. They're shifted. That is what's called a dipole. So let's say we start with one charge-neutral atom or molecule. Okay? It's charge-neutral, but the positive center and negative center are not at the same location. So we say it's polarized, or we say it can be thought of as a small dipole. And here you have another polarized molecule, which is also thought of as a dipole. Now when these two dipoles get close together, what happens? Well, if this is the orientation of the first dipole, it's like this. The second dipole will try to orient the same way, because that way the negative center is closer to the positive center there. So that is a strong attraction. And of course, you also have some repulsion, but the repulsion is less than attraction, because after all, the distance between the two positives is less than the distance between the positive and negative. Okay? So therefore, overall, there is still an attraction between these two through the dipole, it's called a dipole force. Both of these molecules already has a dipole moment to begin with. They're both polarized to begin with. Some molecules are polarized, some are not. Now, another type of van der Waals bonding happens between one polarized molecule and another unpolarized molecule. This guy originally has positive, negative centers in the same location. It's not even a dipole to begin with, it's non-polar. All right, but when you put it close to the polar molecule, you have a positive side here, negative side. So overall, this side would attract negative charge, and it's closer than that. So that means that when you put it closer to a non-polar dipole, a non-polar molecule, the negative part of that molecule, the electrons, would tend to move this way. So the electronic cloud will be deformed to have, it will become thicker on this side because the electrons will try to get closer to the positive charge, and the positive charge on the other hand gets repelled by this guy, so they try to move that way. Doesn't that induce a dipole here? So it was not a dipole to begin with. Now it becomes a dipole, right? And this dipole is caused or induced by that dipole. So we call it dipole-induced dipole force. It's the force between this permanent dipole and this induced dipole. Now the worst case is when neither of these is a dipole to begin with. So neither of it is polar. Can there still be a force between them? The answer is yes, even though it's weaker. That's called dispersion force. Okay, so how does dispersion force work? None of them is dipole. Now, even though they're not dipole, so the positive and negative charges on average have even distribution, it doesn't mean that at a given instant, the positive and negative centers are always at the same location. Okay, the positive may go back and forth, the negative may also go back and forth. So the time average value is in the middle, so it's not polar. But the instantaneous case may not be exactly coincidental. So at one instant you have a positive and negative, the next instant they could reverse. But at that same instant, if this guy has a positive negative, what do you think, what kind of effect would it have on the other guy? Well, the other guy at that instant would probably do something like that, right? Because the positive center, the negative charge is momentarily attracted by the positive center, and like that, right? So you see, you have a temporary dipole here, and there's also a temporary dipole there. So at that moment, they're attractive. The next moment, you never know. They may flip polarities. But as this guy flip polarity, it can also probably cause this guy to flip polarity too, because again, positive charges and negative charges will try to attract each other. So basically, we have flipping dipole moments. Okay, the dipole moments are not permanent; they go back and forth, back and forth. But at each instant, there's greater chance for these dipoles to be for these temporary dipoles to be aligned, just like that, so that we have what's called a dispersion force. So whether the both molecules are polar, one of them is polar, or neither of them is polar, there is still a possibility for them to attract each other through what's called van der Waals bonding. The van der Waals bonding, of course, is not nearly as strong as ionic or covalent bonding, but it's also very important because in some cases this is the only bond you can have. An example is noble gas. In the case of noble gas, the gas molecule is all monatomic because each atom is already happy. It has a completely filled shell. It doesn't want to associate with anybody else by sharing an electron or through electronic transfer. None of these things, right? Does that mean these gas noble molecules will never interact with each other? No, it doesn't mean that, because as a matter of fact, when you cool these gases down enough, even helium, the most difficult gas to be liquefied, will become a liquid if the temperature is indeed low enough. That means at some temperature, low enough temperature, the attractive force between these molecules will actually be strong enough to condense the gas into a liquid. It can even turn into a solid at even lower temperature. So what's the attractive force? Where did it come from? It's the van der Waals force. There is no complete transfer or sharing of the electrons. Another important case of molecular bonding is the so-called hydrogen bond. This is a special bonding involving the element of hydrogen. Hydrogen is the odd one out. As you saw in the elementary table, it is the only non-metal element on the left side of the elementary table, or periodic table. It's got only one electron and one proton. That's it. Having only one positive charge, one proton to attract that electron is not attracted that much by the proton force, because the proton, there is only one proton. If we put hydrogen and oxygen atoms together, the oxygen atom has 8 protons, right? So the attractive force from the hydrogen cannot really compete with the attractive force for that electron from the oxygen. So therefore, even though the hydrogen does not completely give up its only electron, that electron spends most of its time in this region, surrounding the positive nucleus of the oxygen, which is 8 times as powerful as that one proton. Okay, so you can think of the water molecule H2O as a Mickey Mouse. This is it looks like a Mickey Mouse. Okay, and this Mickey Mouse is heavily polarized, with the oxygen side being negative and the hydrogen side being positive. And the hydrogen side has very little presence of the electron. So it's almost a bare proton particle, positive charge particle, positive charge particle. And what happens when you put these hydrogen, when you put these H2Os together? You have another H2 nearby, another H2. Each one is a strongly polarized molecule, right? Very strongly polarized. This side, again, is almost just bare protons, very little electron cloud to shield it. And therefore, as this polarized molecule meet another polarized molecule, another H2O molecule, that other H2 molecule, the negative side, will be strongly attracted to the positive side, made of bare protons, near bare protons, right? So that attraction is pretty strong, even though there is no complete transfer of any electron from here to there. That is called hydrogen bonding. Again, it is because the hydrogen has only one electron, and that electron is almost gone, not complete, almost gone, leaving a bare, essentially bare proton, which can strongly attract the negative side of any other polarized molecule. That's the hydrogen bonding. The hydrogen bonding is not that strong because after all, the electrons do not really run in between these being shared. But it's not all that weak either. It takes about 1/10 of an eV to break it down. 1/10 of an eV. And in the case of water, this is what's responsible for solid ice, water ice to form. The bonding between H2O molecules in ice form is actually the hydrogen bond. And the hydrogen bond is also responsible for some of the unusually large values of specific heat, such as the specificity of water, ammonia, and so on. You know, we saw in physics 1b, water has one of the highest values of specific heat or heat capacity of any substance out of the millions of substances you can find. Water has some of the highest values. Okay, ammonia, in fact, is even higher. The specific heat value of ammonia is even higher. Ammonia also has hydrogen bond in it. So why does hydrogen bond produce such a large value of specific heat? A high value of specific heat means it's difficult to heat it up, right? You have to give it a lot of energy to heat it up. And the question is, with hydrogen bond, why do you need so much energy? The thing is, we're talking about very strongly polarized molecules. They are lined up like this. Okay, you give it some heat, the temperature increases. As the temperature increases, the system gets more and more random, and therefore the alignment is not that perfect anymore. So you have some sort of misalignment. You have, instead of this perfect alignment, you may now have this, or even worse, you may have, reverse polarity. That's what happens when the temperature gets higher and higher. You get more and more random. But there is an energy penalty in going from here to here to here. You have to break that hydrogen bond. Hydrogen bond is not very weak, but it does take energy to break it up. Okay. On the other hand, you have other substances which itself may have much stronger bond, such as diamond. Diamond is incredibly strong. It is the strongest material found in nature, much stronger than ice, and yet the specific heat of diamond is not very high compared with the specific heat of water or ice. Why is that? Because even though the diamond bonding is very strong, we'll see that later in this chapter, when you heat up diamond, you're not really breaking that bond up, okay? Because the bond is just too strong. You can never break it. You're actually just shaking it up a little bit. So the diamond, the carbon atoms would just oscillate a little bit more. You're not breaking this bond. Here, even though the bond is weaker than the diamond bond, you're actually breaking them. You're breaking them apart. If you reverse the polarity, you actually broke this bond. So that's why when you have hydrogen bond, you're looking at typically very high values of specific heat. Water being the most famous example. And as we saw in the textbook, the hydrogen bond is also important in the formation of life because it's what ties the DNA molecules together. The double helix structure is what ties it together, so it is of great importance in life as well. All right, so we looked at some typical bonding mechanism in molecules. And so we now, if we focus on the energy of that molecule, okay, so we have a molecule, and let's examine what kind of energy or quantized energy levels we can associate with that molecule. When we studied atoms, we looked at light coming from the atom, right? And that was the key experimental evidence that gave us quantization of energy inside the atom. Can we do something similar for the molecules? Can we look at light emitted by molecules? It turns out, yes, we can easily do that. We can certainly do that. And depending on different modes of motion of the molecule, we can have different types of light emitted from that molecule. So we're now going to look at modes of motion or states of motion and the energy spectra or light coming from that molecule. Let's do that.